Okay, hi everyone. I'm Adrian. I'm a postdoc at CCA in Princeton, and today I'm going to talk about field level inference broadly, but also focus on some applications to BAO Reconstruction that we've been doing recently. So just to give a quick introduction to field level inference, because I'm the first one talking about it. The aim of the game in cosmology is you have some data, often in the form of a map, and you want to extract cosmological information. Traditionally, people have used the two-point correlation function or the power spectrum, but as we probe smaller and smaller scales and higher resolution telescopes come into play, that doesn't give us all the information. And so people have looked into using higher order statistics. For example, we heard about the bispectrum from David, but some higher order statistics I looked into are the halo mass function and the void size function. And we found in the Coyote simulations that if you combine all of these, you get this really powerful degeneracy breaking. So power spectrum is the red contour, halo mass function is blue, void size function is green. And for neutrino mass of sigma 8, there's a huge improvement by combining these higher order statistics. So theoretically, there's a lot of extra information to be found in the field. And the question is, can we find all of the information? And so this is the motivation for field level inference. And the idea is you start in the early universe where the initial conditions are Gaussian. So every pixel in your field is a Gaussian random variable. You then have some forward model, which takes these initial modes, S, so the forward model is F, and the cosmological parameters sigma 8 and omega m, and it gives you the final field. So it could be galaxies, could be weak lensing, could be the CMB. And another project I've been working on, which I don't have time to talk about today, is the half-dome simulations, where we're producing correlated simulations of the universe that have galaxies, weak lensing, CMB, and you'll hear more about that in Gia's talk tomorrow. So that's very exciting, but just to focus on galaxies. So you have some forward model, could be n-body, could be effective field theory, which gives you the galaxies. And then the idea of field level inference is to take this backwards and infer the initial conditions and the cosmological parameters jointly. And because you're modeling every single variable, this should give you the most optimal constraints you can get on the cosmological parameters. But the problem is, this is a multi-million dimensional problem. If you're trying to infer every single pixel of the initial cosmic field, and you want to do this at a resolution appropriate for upcoming surveys, you're going to have millions and millions of pixels that you've got to do inference over. And so how do we solve this problem? So first, let me talk about explicit field level inference. This is when you write down a likelihood and try and do something like optimization to infer what the initial pixels were. And so some people looked into using optimization to solve this problem, and it works quite well when you don't have a very nonlinear problem. So for example, in CMB lensing, SPT recently put out an analysis where they used optimization and then like a Laplace approximation around the peak of the posterior to do inference over some systematic parameters in CMB lensing. But as you go to galaxy clustering and weak lensing, this no longer works so well. It's too nonlinear of a problem. And then you've got to move on to Monte Carlo sampling. I think we'll hear a lot about that in this workshop. But just to talk about one particular kind of Monte Carlo sampling that I've been working on recently, there's a method called microcanonical Langevin Monte Carlo, which seems to perform more efficiently than Hamiltonian Monte Carlo. So here's an example on the dark matter field where we're looking at the efficiency of the microcanonical sampler to traditional Hamiltonian Monte Carlo. And you can see as you go to higher and higher dimensions, the efficiency compared to HMC gets higher and higher. So if we want to scale Monte Carlo sampling field level inference to higher dimensions, this is a really useful method to use. And recently, Hugo, Simonon-Foray, and Francois have shown that this also extends to bias traces. So here, lower is better, and you can see that the green line, MCLMC, is performing more optimally to other methods people use for sampling. And then also, recently, we've been applying this on the curved sky for the CMB. And so this plot is showing the effective sample size. So higher is better here, and you can see MCLMC, the yellow dots above the other sampler. So this looks very promising moving forward. But the big question with explicit field level inference is, what is the likelihood? We've got to make some assumption about the likelihood that we're sampling here. Often it's a Gaussian assumption, and it's unclear whether that's valid as you go to smaller and smaller scales. So to move past this, we can do implicit field level inference, where you use a neural network to learn the connection between your final field and the initial field, or the cosmological parameters, or both together. And so one way you can do this is with diffusion models or stochastic interpolants, and this is something that I was looking into with Carol. where we looked at how many simulations you need to use a diffusion model or stochastic interpolant approach to match the results of HMC. And so this plot is showing the cross-correlation coefficient, so the quality of the field level inference, the reconstruction, for HMC in the dashed line and stochastic interpolant in the solid line. And you can see that you need around 10 to the 4 for these two lines to converge to each other. And I think Carol will tell you more about this tomorrow. But just to show you what a diffusion model is, in case you don't know, the idea is you have some images, for example, of a mountain or Mount Fuji. You add noise to it step by step until you end up with pure noise. And then the idea is to use a neural network to undo this noise. And so in the cosmological context, you're trying to go from the noisy initial conditions of the universe to, say, the final universe. So let's have a look at this in action. Here's a picture of me and Carol actually at Mount Fuji, but it was very foggy, and we couldn't see Mount Fuji. So we were very, very sad. But with a diffusion model, Mount Fuji. But you don't have to apply this to Mount Fuji. You could apply this to the real universe. And we're very excited about that. But another thing I'm very excited about is just using a CNN as a point estimator. And so this is work with Liam Parker, a grad student at UC Berkeley. And what we're trying to do here is just go from the galaxies field to the initial field of the universe for the application of BAO reconstruction. And so what is BAO reconstruction? In the linear early universe, you have this very beautiful circle associated with the BAO scale. But then, as nonlinear evolution happens, the circle starts getting distorted, and you get this black fuzzy line. And so what you want to do, and what people have been doing for many years, is to try and reconstruct the BAO. So to undo this nonlinear evolution and get a much cleaner view of this circle. But you can see over here that the reconstruction in the solid line hasn't quite reached the dashed line on top. And so there's room for improvement over traditional BAO reconstruction methods. And so what we did in this project is to use a CNN to improve the reconstruction. So the idea is you have the galaxy field, and this is based on simulated galaxies. You then do BAO reconstruction, so a traditional BAO reconstruction based on Zeldovich approximation. This gives you the correct large-scale reconstruction of the field. And then you feed both of these into a CNN to learn the small-scale corrections to the reconstruction. So the reason for doing the BAO and the galaxies into the CNN is to give the CNN an idea of what the large scales are, and so it doesn't have to work so hard to figure out the small scales. And on top of that, you can use, you're trying to infer the true linear field. On top of that, you can use a subgrid approach, because if the large scales are correct from the BAO reconstruction, all you have to do is train your CNN on small patches of the sky. And because you're doing this, you can then scale this up to much larger volumes. So even if I trained on a 1 gigaparsec box, I can learn these like small scale tiles of reconstruction and then tile a much, much larger volume to do reconstruction on a much larger volume. So let's have a look at this in action. This is a plot of the cross-correlation coefficient. Standard reconstruction is the gray lines, and the different line styles are different angles to the line of sight. So you can see those are the lowest lines. They have the lowest cross-correlation coefficient. Then when you add the neural network, you get the orange lines, which improve the cross-correlation coefficient to smaller scales. And the blue line is showing as if you had no redshift space distortion. So because the solid orange line is close to the solid blue line, that means even when we have RSD, we're doing as good a job as we can to reconstruct these initial conditions. So this is when we trained on 1 gigaparsec and tested on 1 gigaparsec. But how does this scale up if I test on a 3 gigaparsec box? And so this plot is showing now, solid line is the 1 gigaparsec application, and the dotted line is 3 gigaparsec application. And you can see the solid and dotted lines agree with each other perfectly. So this is saying that the method scales up to larger volumes without any loss of quality. So that's very promising, scaling up to volumes like DESI and Euclid. Then, given this better quality reconstruction, the next question is, what does this mean for the BAO? How well can I measure the BAO scale? So this plot is showing the Fisher information in the log of the BAO scale. And you can see for traditional reconstruction in gray, it's quite low. With the CNN, you get a much, much higher Fisher information in the orange line. And then the solid line is like, if I could actually measure the full linear dark matter field, that's how much information I can get on the BAO scale. So there's still room for improvement, but so the orange line is improving a lot over traditional BAO reconstruction. And so now we're applying this to DESI-like mocks, doing a full BAO fit in the initial reconstructed field that we've made. and then finding the constraints on the BAO scales. So you have this parallel and perpendicular direction of the BAO scale, which can also be summarized as QAP and QISO. And so some preliminary results we have on LRG, DESI LRG-like galaxies. For standard reconstruction, you have this 0.01 constraint on QISO, for example. Then with explicit field level inference, so writing down the likelihood, you have a 4% improvement on that. And then with the CNN, implicit field level inference, you get a 16% improvement. So this is very exciting, and we're working towards applying this to real data. And another really nice thing we did here is coverage tests. So very often when you do field level inference, it's so expensive, you just apply it on one simulation, it kind of gives you the right result, and you're like, okay, good job. But here, I ran 1,000 simulations and did field level inference on all thousands of these, and checked that the error bars you get actually are well covered. So the 60% confidence interval is actually covering the truth 60% of the time. And so this gives us promise that the methods we're using are doing the right thing and are well valid. More generally on this point, one question when you do field level inference is you have to train on some simulations, but does that generalize well to other simulations? And so in this project, we were doing a field level of comparison of different n-body simulations. And in this case now, I'm not reconstructing the initial conditions, I'm just inferring the cosmological parameters by doing field level inference. And so here you have a whole range of different n-body simulations, Gadget, Abacus, QP3M, etc. They look quite similar by eye, but if you take a ratio of these fields, you can see there's quite a large difference between the two. In particular, Ramsey's has a lot of red and blue, very sharp red and blue, implying it's very different to Gadget. And so what does this mean when you do field level inference? Here's a plot of the inferred, like omega m on the left and sigma 8 on the right. So the inferred minus the truth. And so you want a straight line that agrees with the horizontal line. And you can see for Gadget in gray, it agrees pretty well. For Abacus, agrees pretty well. But then for Ramsey's, there's a huge difference between the inferred value and the truth. And so this is saying that there's some difference between these two n-body simulations. And what it is algorithmically is that Ramsey's uses adaptive mesh refinement, whereas Gadget uses a fixed grid. So Ramsey's resolves small scales much better than Gadget does, and also smooths over large-scale voids, for example. And so if you just apply your CNN, trained on Gadget, and applied on Ramsey's, you can get very bad results. And the reason for this can be found by interpreting what CNNs are learning. So what you can do when you train a network to, say, infer omega m from some density field is take a gradient of the network output with respect to the input. So how much does my output of the neural network change as I change the input a little bit? And you can get a map that looks like this. Black shows you have a high response, white shows low response. And so this is saying that the neural network is paying a lot of attention to like really overdense regions and also really underdense regions. So it's looking at like the halos, the clusters, and the voids. And so because a code like Ramsey's resolves these objects differently to a code like Gadget, when you just take your CNN from one and apply it to another, you get biased inference. And so the solution, or one solution, is to smooth your fields before you apply a CNN. There could be other approaches as well. But what we found is if you smooth by 6 times delta R in the top, so 6 times the grid resolution, then your constraints on omega m and sigma 8 agree between Gadget, Ramsey's, and different variants of Ramsey's. And so, yes, you've got to smooth your field before you do field level inference. Another way you can look at this is at the actual data vector level, and maybe I'm running out of time, so I won't explain the details, but very happy to chat about this later. But there's this really cool method called PQMass, developed in Montreal, where you can compare 2 distributions, 2 samples, and check whether they're in distribution with one another. And so if you do this initially to the simulations in question, you can see that Gadget, the histogram agrees very well with the line, so it's in distribution with itself, which is very good. But then all the other simulations are disconnected from the solid line, implying they're out of distribution with Gadget. But then if you smooth the field, everything agrees. So this is a really nice diagnostic you can use to check whether 2 simulations are in distribution with one another. Another thing I've been working on recently is transfer learning, and this is a way to make things more efficient. And so, for example, if you want to do simulation-based inference with an n-body simulation, perhaps you're looking at modified gravity, that could be very expensive to run a lot of simulations to do this. And so, one question you could ask is, what if I trained my neural network on a fast simulation like FastPM on lambda CDM, can I then transfer it to an n-body simulation with more complicated beyond lambda CDM cosmologies? And if you can do that, then you can get away with running less complicated n-body simulations and improve the efficiency. And so some results recently. So here we're going from FastPM to Cahote, so a low fidelity simulation to a high fidelity simulation. The plot here is showing the negative log test probability, so lower is better. And you can see if you're only trained with the high fidelity simulations, you have this red line, which is quite high, all the way down to 10 to the 4 simulations, which is a lot. And then the blue line with transfer learning is lower. So you save a lot of simulation budget by doing this transfer learning. And then some preliminary results also is going beyond the standard model. So here we're looking at the power spectrum, and we trained on, for example, you could train on no lambda CDM simulations in black, and then just do your inference beyond the standard model, so with neutrino mass and f of r, and you can see the black line is where it is. But then if you pre-train on some lambda CDM simulations, you get the blue line, which is lower, and pre-trained on even more lambda CDM simulations, you get an even lower line. So this is quite a promising approach to improve simulation efficiency. And that is my last slide. So just to summarize very quickly, field level inference is great. We want to try and get optimal constraints, but we've also got to be careful to make sure things are robust, interpret what we're doing, and also be efficient. Thank you very much.